Let's discuss now the physics of heat. The first idea is that heat is just a transfer of that hotness. So we have two elements together in contact, and we see that one of those has certain hotness or certain temperature, and the other one has a lower temperature. But when we put them in contact, at the end they reach an equilibrium according to the zeroth principle or zeroth law of thermodynamics, which defines thermal equilibrium, in a temperature which is between both of those. So we know that therefore, or we see then that the heat or the energy is being transferred from that hot device, from that hot object to the cold one, right? So this is something that we will answer why later with entropy. For the time being, we're interested in seeing that there is this transfer, and we want to somehow quantize this. Now, this presents, of course, a problem, because how do you quantize what's that heat? And the answer is going to come, or particularly, there's some ideas of what is heat, and historically there's the idea of caloric. It's a classical device, so to speak, of physicists to introduce invisible fluids to account for certain properties, for certain material properties, because at the end of the day, it's a materialistic, in a way, approach to nature, and so we want to posit that there are things, material, even if they're massless or invisible, that somehow are being transferred from one to another. In the history of medicine as well, there are many of these humors and fluids that account for many different things, right? And the idea of caloric is precisely that, which is endorsed by some guys, some great geniuses like Laplace or Lavoisier. They're thinking like some materials have certain amount of caloric, which if you can think of an invisible and massless fluid, and that's why they're hot. And you transfer some of that to something else, and that something else increases its caloric, and so it becomes more hot. This is an idea that's also similar to the one that was developed for charges, right? And when they were started to analyze electrostatic fields and so forth, as you will see in physics too. Now, caloric is going to be disregarded. It's going to be completely displaced out as soon as we are going to see Count Ramford and James Prescott Joule came with their experiments. The experiment of Count Ramford is actually pretty interesting, because he realized when he was boring cannons on the arsenal in Munich that the metal was getting really hot. And then he envisioned an experiment where he could put a dual boring tool and a piece of iron underwater and start making, basically like you imagine, start to mill or try to mill that thing, but because it's dual, it was not really milling anything. But he realized that the water was getting warmer and warmer, and he realized that in 2 hours and a half, about that, I think it was, he started to see the water boiling. And so he had this first intuition. There is no limit on how long I can be doing this. And so the heat cannot come from the boring tool, because that would require to be infinite amount of that if I can keep going forever. The thing that's missing there is that it's actually the motion of the horses that were actually moving the boring tool that's actually responsible for that. And James Joule is going to come, with an experiment to try to quantize that. And his experiment basically is just to have, let's say, a bucket with water, and let's say that there's some paddle wheel in here, and attached with some pulley system maybe, there is a weight hanging here. You let the weight fall, and so this thing starts to rotate. And so if you calculate what was the energy at the beginning, and you calculate what's the energy at the end, if there was nothing in here, we would expect that the change, if the mass was just free to fall, right, it would just come to fall, and then we will say that the change in energy, which was total energy at the beginning minus the total, or the total energy, at the end minus the total energy at the beginning, that should be zero. But if you observe that there is a change in energy between the beginning and the end, as we observe in here, this is free fall. But if we observe in here, you can calculate the change in energy, and suddenly you realize that when you calculate the total energy exchange from the ball being here or the weight being here and there, total 1, right? What he observed is that this is different from 0. In fact, there is a loss of energy. This was negative. So where's that energy going? This is mechanical energy that is disappearing. Of course, this is connected to this. And he realized as a result of this was getting warm, because that's the idea of Ramford. Ramford is saying there's mechanical motion producing heat that cannot be a fluid. And what Joule is going to do is actually find the mechanical equivalent of that heat by basically this. We said that the change in energy is equal to work. Now we're going to say that the change in energy can be, of course, work, but in this case there's nothing in here making the work, in a sense that change in energy is going to the water. And if that is the case and the water is getting hotter, this transfer of energy is what we're going to be calling heat, which is what's responsible for being hot. And so I can say that the change in energy is not just simply work, it's also heat, with Q being heat. Now it's interesting to notice, and we're going to get into all the details, that this is the classical way of being the problem, writing of this equation for chemistry, which is the UPAC criteria, that takes that work on the system is positive and work done or work extracted or work done by is negative. Heat transfer to the system, we're going to take positive, and heat taken, no, or heat done or heat transfer from, we could say, right, that's going to be negative. Sometimes you find this negative because the sign is inverted. We're not going to take it that's Clausius criteria. I think this is much more intuitive, because we're going to take a system and we're going to say this system takes work, work is going to be negative. Someone puts work, work is going to be positive. This is what we just said before. And now we're just going to say if I transfer heat in, it's going to be positive. If I extract heat from the system, it's going to be negative. That's, I believe, a better way of approaching this problem to see this. It's going to help us seeing that balance easier. So in a way, then we have the mechanical equivalent, as it said, of heat. If now I account for heat, then this is going to be 0. So now I know this is not different from 0. There is no work. Why is this not different from 0? Because there's heat. And now, because I can calculate the change in energy, basically because I know the energy at the beginning, which is fully potential, and the energy at the end, which is no potential but it's kinetic, what is the difference? Now I can mathematically and numerically quantize that change. That change is exactly giving me heat. And heat, of course, is going to have units of joules, right? The heat is going to have joules because it's energy. So it's important to see objects do not have work and they do not have a heat, right? Objects or systems can do work and can transfer heat. So heat is just the transfer of energy, and there's a thing to say there is the transfer of energy as a result of a difference in temperature. That's the definition of heat. And so with joules, we have a way actually to start to mechanically quantize this, and we have a way, excuse me, of quantizing that, and we have a way of actually putting numbers. From this, we can build all the calorimetry experiments, which is all that we're being interested in this course for this this section on heat. Last thing to say, this is conservation of energy, and this is, of course, first law of thermodynamics. The change in energy is going to be due to work, and it's going to be due to heat. This concept is going to be very important to develop then on next video on entropy, all the ideas of engines, because historically this was the way that it was being presented. One last thing that we can say on how heat works, which is important, is to say we have the microscopic approach to this. And what would that be? Well, basically imagine that you have two objects in contact, right? And one is at a higher temperature than another. Let's erase here. So you have an object with a certain temperature, we put in contact with another one, right? This, let's say, is temperature hot, and this is temperature colder, because the hotter temperature is larger than the colder one. And we put them in contact. We expect that when there is no more change, zeroth law, they're going to be in thermal equilibrium. And so we're going to find that the equilibrium temperature is larger than the cold one, but the equilibrium temperature is smaller than the hot one. What is temperature? Temperature is a measurement of the average kinetic energy of the particles. And if it's an ideal gas, there's no other source of energies in here, so they're just simply moving all over the place. So what's important from here is just to realize that then what's happening, what I'm telling actually is that temperature is proportional to the kinetic energy, to the average kinetic energy, doesn't matter, square root of whatever. What's matter is this saying this thing is the kinetic energy, right? Excuse me, and the velocity is going to be the square root of, right? So the velocity is proportional to the temperature. So what we're interested in here is saying that there is high temperature. It's another way of saying there's a high internal energy of the particles, but that means that those particles are moving faster. So what happens if I observe this, let's say molecularly, at the molecular level, I'm going to have a lot of particles in this system that travel with a lot of velocity. They're moving randomly, certainly, but they're going with a very high velocity. Whereas if I have a system here which is cold, I'm going to have particles, but they're just barely moving. So what happens when I have them in contact? That these particles are going to start coming very fast and transferring their momentum through the collision to the other particle that is moving slowly. And so slowly these ones, after these collisions happen, after some collisions happen, what I'm going to start observing is that these particles then reduce their velocity because that energy has been transferred to the other one that now has larger velocity. And slowly the velocities equalize, and that's when you reach the thermal equilibrium. So now we also see how heat transfers, and why we can even see that heat transfers from hot to cold, right? This becomes very fast. Here's the other one and goes there. Why? In reality, we're going to answer again with entropy, because there's nothing in here with respect to conservation of energy that says that you couldn't have a particle coming here and then even getting more velocity from this interaction. Okay. Now, last thing to say in here, of course, is the idea of internal energy, but we will discuss that probably in the context of calorimetry. So let's erase this and present those ideas. Now, in an ideal gas, we said that the only type of interaction that happens in the molecules, first of all the molecules are identicals, and they just happen by transferring energy through elastic collisions. So we said that the entire energy that we're measuring with temperature, which is the kinetic energy, the average kinetic energy, is due to this translation. What happens when you have not anymore single molecules like you have in an ideal gas, but you have maybe diatomic gases, when you have complex molecules, molecules with a certain structure? At that point, you cannot just make some assumptions anymore. What's happening there is that we're going to start saying that there is other modes that are available for the molecules. For instance, we said it before, but the molecule of oxygen, which is diatomic, has 2 atoms of oxygen, right? You have oxygen and oxygen here, and so you have O2. This molecule can certainly translate around, so you can see that the molecule at the time later is in here, right? But you can also see this is going to be, of course, kinetic energy translation. We said that. And we also said that because this is a solid, we can expect that the molecule starts to rotate. And so we're going to say this is the kinetic energy of rotation. It turns out, and we will see this in the next chapter, but there's also another way that we can say that the objects can vibrate in this case. And in vibration is interesting because what happens in vibration is that the center of mass as such does not move. So it's not the same as translation. I mean, if you take a single particle, this one is translated, but the entire thing is actually just vibrating. So the center of mass doesn't change. And then we have to account also for vibrational kinetic energy. We'll see this in the next chapter with a little bit more detail to introduce the idea of waves. But any particle in general, any complex molecule in general is going to have kinetic translational energy, is going to have rotational kinetic energy, it's going to have vibrational kinetic energy. All of these ones are going to be accounted by the idea of temperature, right? This is the first thing, but this happens in the case of gases where particles are free to move. As soon as you go from gases to liquids, and even more to solids, of course some of this may or may not apply anymore, but in the case of solids in particular, particles are not much rotating or with translational energy. Most of it is going to be purely vibrational because they're solid, they're rigid in place, so they're bonded strongly one atom to the other, right? So when you have a solid, for instance, what you're going to observe is that you have particles here and here and here. And so what you can see these particles doing is kind of vibrating in place, right? So you could expect them to be just maybe vibrating here and there with respect to their original position, right? So they're just kind of vibrating. They're just not moving around, right? So the temperature is going to be kind of telling you that, the idea of vibration, because the rotation and the translation is going to be an ideal one, nothing, but there's nothing ideal in the real world. So this is important to consider. But in the case of solids, and in the case of liquids, you don't only have any more particles independent moving all over the space. They're not anymore that assumption we say that they're far apart from each other. Now they're actually colliding with each other much more frequently because we are making them more compact. That's why we said that the density is increasing. So as we go from gas to liquid to solid, we are compressing them, we're kind of increasing the density. They're more compact, they're going to start interacting more strongly. And when they interact strongly, what they start to have is forces, which are going to be electrostatic forces, which are responsible precisely for those chemical bonds that develop between the molecules. And those bonds are also taking energy. So when we describe what we call the internal energy of the system, we're going to have to account for the kinetic energy, but we're also going to have to account for the for the potential, and we call this chemical or binding energy. So this is the important thing. Kinetic energy can be translational, rotational, or vibrational, and that's going to be the temperature one. But liquids and solids also have to account for certain binding energy of the molecules interacting with each other. This is a premise that was, or this is an idea that was completely prohibited, so to speak, in our postulates of an ideal gas. They say they do not interact. There is no electrostatic forces between them. Electrostatic forces, again, you will study it in physics too, but you have some ideas already probably from general chemistry. So they interact with each other from other means, which is not just simply colliding, because some effects in there. And they can even bind together, right? So this is something that doesn't happen in the case of ideal gases, but happens in case of some on liquids and solids. And so this is an important distinction to say how much energy has something is actually going to be described by that internal energy, and it's going to be the kinetic energy from our perspective, again, obviously disregarding any relativistic effects, right? So it's going to be kinetic energy and the chemical binding energy of the particles. And why is this relevant? Because we're going to observe two different things when we're making analysis. These laws, or these equations rather than laws, which are the ones for calorimetry, we can define this calorimetry, which is the science of studying precisely calor, which comes from caloric, which is the same root for calories, which is heat, right? Some of these ideas developed before even there was an idea of particle physics for that, kinetic atoms, right? The molecules moving and being responsible for everything in matter. So these are macroscopic observations anyways. So we're going to observe two things. If I have a glass of water, and you can make experiments with calorimeters, and we're going to see some next. You say you have a bucket of water, and you have two waters, let's say with the same temperature, and you throw two objects in there at different temperature, that the equilibrium might be different. And so you start to see that the transfer of this energy, this hotness, is going to be proportional to how much matter there is. It's going to be proportional, the transfer of heat, we say it's going to be proportional to how much matter there is going to be proportional of how, or the initial temperature, and it's going to be also proportional to the particular material that you have in every case. And that's going to be given by this equation, which is going to say is proportional to the mass, is proportional to a coefficient that we call C, which is a specific heat, and is finally proportional to the change in temperature, which is obviously final temperature minus initial, and this is the mass. We can understand each one of these concepts together. Why do we say mass? Remember, everything is made out of molecules. If I have a higher mass, I have more molecules. So how much heat do I need to heat up something to the same kind at the same temperature, right? Y mass, let's say Y mass is the number of particles. So if I want to impart to each particle average kinetic energy corresponding to this delta T, then I need to provide more the more particles there are. If I want every particle to be with 1 joule, let's say, of course that's crazy, but let's say 1 joule, and I have 1,000,000 particles, then I will need 1,000,000 joules. Whereas if I have 500,000, I will need 500,000 joules. So then I need more energy, more heat to actually achieve the same thing. Now the second concept, of course, is the specific heat, and this boils back to the type of material that we have. So depending on the type of material, you're going to have a specific heat or another. In thermodynamics, typically is described is divided between specific heat at constant volume or constant pressure. We're not going to make these distinctions because we're more interested in the concept just as an introduction. But the specific heat is telling you, depending on the particular atomic structure and how the material behaves, transferring heat is going to be easier or more difficult. And it makes sense if particles are very far away, or they're condensed, or how are they binding together, right? This is the idea of a specific heat, which just tells you the type of material. And finally, we have delta T, which is of course T minus T sub 0. It depends basically on the initial temperature, right? So how much heat do you need to raise water at 10 Celsius is different if originally it's at 1 Celsius or it's at 9 Celsius. Because if you're at 9 Celsius, then you only need to increase 1 degree, so the delta T matters. So this is kind of trivial. You want to put certain energy, how much energy you have to begin with is going to be relevant. And so this is the idea for this equation for calorimetry that we can understand again from the microscopic perspective. But there's another thing that we can figure out in here, which is interesting in calorimetry. If I have a bucket of water and let's say instead of a bucket of water, let's say I have over here, I have a piece of ice, a very large one, and I somehow just put a thermometer in here, right? This is a thermometer. And I realize this is okay, this is at minus 20 Celsius, let's say. Originally, this is initially is a minus 20 Celsius. So what's the idea in here? If I start to put heat in, maybe because I put a hot plate, or maybe because I put it on the fire or something, and somehow I can calculate how much heat I have, and now I can do that because I could put just, for instance, the same fire or similar system with water and measure how the water is changing, and so I have basically a way of calculating the heat, right? So now I know the different change. I can calculate 1 calorie is how much heat energy you need to raise 1 degree, 1 gram of water. That's the definition, right? That's the definition of calorie. So now I have a way of quantizing how much heat I need, and so I can calculate for that much heat what's happening in the temperature. And so I can find that for ice, what I'm going to observe as I go, let's put it in here. As we increase, as we add heat, let's say, I'm going to observe how the temperature changes. We can actually add delta T in here. And what we observe that maybe even we start at minus 20 degrees, as we add heat, of course, what we expect is, according to this, the change in temperature is going to be, with heat, is going to be proportional to mass and this. The mass is the same, it's the same block, so it's just going to be proportional to C, let's say, right? Okay, but at some point, I see that the temperature goes, let's say, minus 20. It goes all the way up to maybe, let's say, 0 Celsius. What happens at that point is that as I add more and more and more heat, I do not observe any change in the temperature. The only thing I observe is that the ice starts to melt and becomes a liquid. And only when, in an ideal, again, world, but this is a good approximation for us anyways, and only when all the water has melted, then I start to see that the water liquid starts rising again. And with more heat, it raises the temperature. And suddenly we reach a point when this is 100 Celsius. And when I reach 100 Celsius, the same thing happens. The object, I add heat, I add more heat, but the temperature doesn't change. More heat doesn't change, more heat doesn't change, more heat doesn't change. And suddenly, it starts increasing. What's that point in there? What's that last step in there? Well, that step in there happens at 100 Celsius when all the water has become vapor. And so that's what we say, that in here, in this region over here, right, in this region over here, we have a gas. In this region over here, we have a liquid. In this region over here, we have a solid. And everything in between are mixtures of both of those. So here's the thing. Heat is transfer of energy. As I'm adding energy, I'm increasing the motion of the particles. No problem. I'm adding energy, internal energy is going to be increasing on the energy, kinetic energy. What happens when I reach here? Why when I add more, this doesn't change? Where is that energy going? The energy is not being lost. The energy is being used to break or make, if it's the opposite process, these chemical bonds. So if I add more energy, and now I'm capable of breaking the bonds. Imagine that you have an atom, as simply as saying we have one atom attached to the other with a spring or something like that. What do you have to do if you want to break this? You have to start pulling from this, applying a force for a certain displacement until this breaks. And what is a force times a displacement? That's work. And remember, work is equivalent as heat, it's just energy, right? So you can make the equivalent, let's say, of heat. So what you're actually saying is, if I want to break the bond, I need to do work on the system. If I want to break the bonds that keep the object solids or liquids, I need to add heat. So this flattening here is because all the energy that you're transferring into your system as heat is being used to break in the bonds. So the solid starts to break those bonds, and the same thing is going to happen going from liquid to gas. And contrary, if you had a gas and condense it, what you're going to start seeing is that you have the opposite thing. So as you extract heat from the system, right, it will be in this direction. So we were extracting heat from the system, we reduce the temperature, we're extracting this energy. But at some point when it reaches the 100 Celsius, the energy that we extract is not anymore extracted from the motion of the particles, which is the temperature, is being extracted from the bond. So we start to produce bonds, and so the system releases energy. And this is the idea that's going to be used, for instance, in sweating. When it evaporates, what happens when the liquid becomes gas? Where you're absorbing heat from your body, and so the body loses heat. The loss of heat on the body represents a negative heat, which is going to represent a negative change in temperature of your body. So you can regulate your body temperature by means of by means of perspiration, basically, right? Which is just making that thing. And something similar happens, for instance, in the AC systems. There are some subtleties in there we will not get into, but basically the idea is that, let's say, if I have if I have a liquid and I expand it into the gas, then I'm having a phase change. So I'm going from liquid to gas. So I need to provide the energy to break those bonds. So where's that energy coming from? That energy is coming from heat inside the house or inside your car. That energy transfers to the freon, in the case of, that's how it's called, freon, the gas, typically. Other systems, but you can use typically freons, let's say. That heat from the room or from the car goes into the freon then becomes a gas. But that heat has been lost in your house, which means that this energy is negative now. This heat is negative, which means the temperature drops in your house. That's how AC systems work. So this is this idea of transfer of energy. And mathematically, we can find that, of course, how much heat you need for that. We can call this Q sub S for a specific and Q sub L for latent. heat, right? Because it's just kind of underlying, there's latent, it's just in there, right? That is proportional, of course, to the mass, and then what we call this latent specific heat, which is a constant that depends on the material. This is the second equation that we need in calorimetry. Of course, how much energy you need to do is going to be proportional to the mass, which is again proportional to the number of particles, because the number of particles is going to tell you the number of bonds that you have to break. So the more bonds available, the more energy you need to do to break them all. So it's going to be proportional to the mass. But it's also proportional to the type of bonds that you have, which is somehow enclosed with the type of material which is enclosed in that constant, the same way that we enclosed it for the just change in temperature with a specific heat. So we see the complete picture of how heat works. Heat is just transfer of energy and describes why things become hotter, which becomes higher temperature. But because we also understand the way temperature works, which is microscopically that thing, we can understand how things in contact with each other can carry that energy through collisions. For instance, or vibrations just vibrating. If there's another solid, this one is going to be vibrating, and that's going to be like a chain reaction, that, like a domino effect that transfers that vibration all over, which is what happens, for instance, in conduction. If you take a metal bar and put it by the fire, it takes a time for the heat for the temperature to raise. It kind of radiates from or goes from the fire source to your hand, right? If you're grabbing a bar here of metal and you have a fire in here, this starts raising the temperature and this thing starts to advance like this, right? It just goes towards there. It takes a while because the temperature of the particles are hitting each other and they're kind of warming up by collisions, and it needs to transfer all the way here. The last thing that we can say, but this is more conceptual, we're not going to have applications in here, although there are equations for those. We're not going to take them in this course, but there is three ways in which energy as heat can be transferred. The first one is conduction, which is solids in contact. The second one is convection, which requires fluids, whether gases or liquids. And the last one is radiation, and radiation is just simply electromagnetic light. You will see why radiation is one of those in physics 2 when you introduce the radiation of electromagnetic waves as the result of charges accelerating and decelerating. So those are eventually also related to the kinetic energy of charged particles. But basically, this is just the idea we want to say. There are different ways conceptually in which you can transfer heat, but at the end of the day, all of that is a display, or is a case of the same nature of the same process, which is just the transfer of energy. So we know now calorimetry for increasing the temperature, we use this. Whenever we reach the freezing point, the boiling point, one of the transition points, then we're going to have to count the heat required to break those bonds. And once we've broken those bonds, now we're again back to our previous equation. So let's see some numerical examples, very simple but very interesting. Let's solve the first problem, and this one is problem number 1 in the discussion. And this is interesting because this is kind of a situation where you're going to find when we indulge in one of those guilty pleasures. So let's say this is you, and you're going to be the system in this problem, and the question is what happens. Well, let's read it. But it says you throw caution to the wind and eat 500 calories, and note the capital C, right? So the big C, the uppercase C, of ice cream and cake. To compensate, you want to do an equivalent amount of work climbing stairs or a mountain. How much total weight must you climb? So this is the question we're asking. How much work do I need to actually do? So basically, what's the height I need to climb to produce such a work that burns these 500 calories? First thing that we're going to notice, let's maybe make it in here. The first thing we're going to say is just the units change. In food, 500, the calories for food actually are what we call kilocalories with lowercase in physics. So capital CL is 10,000, or excuse me, 1,000 lowercase calories. The second thing we're going to say, which is going to be important, is that 1 calorie is 4.18 joules. 1 calorie again being the energy required to raise 1 degree Celsius 1 gram of water, by definition. And this is the way that we define the calorie, right? And the next thing we're saying is that, of course, then 1 capital case calorie, which is the calories in food, that's going to be, of course, 4,000 or 4,180 joules. Okay. Now, why do they do that? Good question. But anyways, do not even dream that by eating only cake and ice cream, you're only taking 500 calories, and you say, oh, that's fine. No, it means 500 calories in food with uppercase C, which is 1,000 times a calorie in physics. So in reality, you're actually eating 500 times 4,180 joules. So what we have to see is that you're eating, right? The energy you're eating is 500, 4,180 joules. And that's the energy that you're eating. So that's how much? Turns out to be 2 megajoules, or 10 to the 6 joules. Okay? Now let's analyze the system. This is you. And this is the cake. Let's say it's your birthday. And the cake is coming in the system, and the question is what's going out. If the cake comes in the system, increases energy in the system. But we want to make sure that what comes in goes out. And in this particular case, goes out in the form of work, because we want to climb a mountain. So we're gonna just saying, okay, I'm gonna go eat this, and that represents me going from here to here. And the question is how much, in this case, how much sports do you need to play to actually burn those calories, etc., right? So, by the way, whenever you read the packaging or labeling of your food, make sure if it's written with uppercase, that means kilocalories. If it's written with a lowercase, then you're gonna find these kilocalories. Excuse me, you're gonna find that, right? So it's the same. So it's important to make the distinction. Both things are possible, but in the food industry, this is more common notation. Anyways, it's a kind of silly notation, but there's many things about food industry that are not that nice. Anyways, so the cake comes in, the work works out, and we want to have that in balance, because we know that there's a change in energy. What's the change in energy of me eating the cake? Is that I have a cake more. So I have a change in energy that is the energy of the cake, which is 2 times to the 6 joules. And whenever I have a change in energy which is non-zero, that's because there's a change in energy that needs to be equal to work. I mean, in this case, it's not the case, right? So in this case, there's a change in energy because the work, let's say work in is eating this thing, right? But basically, the change in energy, how am I going to burn that heat? Well, I'm going to have certain energy here, I'm going to have certain energy there. What's changing in here is, of course, the potential gravitational energy. In here, potential energy is 0. In here, potential energy is going to be mass GH. Now, something we should say at some point is what's the mass that we're taking. Let's take 60 kilograms, but you can take your own mass, and then you figure out your own how much exercise you need to do for this thing. Or if you're eating something else, read the packaging, calculate the calories, and see, oh, how much am I going to have to work to take care of this, okay? Very good. So what is the difference in here is MGH. So what's the work that I need to do is MGH, okay? So now I'm trying to figure out precisely that, the height. So I need to do work enough to account for 10 to the 6 joules, which means that my mass, which is, let's say, well, let's do it first symbolically, the mass times G times H needs to be 10 to the 6, which is another way of solving for H. We're going to say that H is equal to 10 to the 6 divided by mass, which is 60 kilograms, times G, which is going to take 10, right? Let's take G equal to 10. Don't need to bother much about this. You ate the cake. Let's not get now. Okay, so 2 10 to the 6 and then divided by 600. So that's going to be 2 10 to the 6 divided by 600. If we make these numbers, we're going to find that this is equivalent to 3,003, basically 3,000 meters, 3 kilometers. Now this is quite a mountain, so that's a lot of pastry. There's something fortunately happening here, however, or unfortunately, depending on the circumstance, which is our body burns energy by doing work, climbing the mountain, but also does burn energy, or does burn energy, if you wish, by the mere fact that we are alive, because there's a lot of functioning, all the cells doing work in their body, and you have to keep certain temperatures, etc., right? So those are actually burning heat. So the available heat that you have after being alive, let's say, is usually about 20% of the amount of heat that you produce. Let's say the efficiency is 20%, which actually means that works in your advantage, because for the 500 calories that you're eating, or kilocalories to be physicists, excuse me, we're going to only have to burn 20% of that. So if you take 20% of that, that's going to be, let's say, efficiency, we could just say is 20%. And so we're going to actually need to get 20% of this, which is going to be 660 meters. So that's much more doable. So you only need to climb 660. You could do the same thing of saying how fast do I need to run for how long, and you could, these calculations now you can include them in your diet calculations whenever you're trying to achieve something, or like a particular diet for sports or something. So these are the ideas. At the end of the day, that food is going to be, as you know, with ATP and all those things, is going to become energy for the body, right? Energy available for the body. So that part of that, only 20% of that energy is going to be able or to be used for something else. If you were not to burn those 660, then you're going to start accumulating that energy, typically in the form of fats, that they will be the storage, your battery, for an event where you do work for higher energy than the one that you're taking, and so you start to burn those calories. So that's the idea, basically, right? At the end of the day, it's conservation of energy. So you're going to lose weight usually no. If you want to lose weight, you have to burn more calories than the ones you take. There's no other way around it, right? So either you eat less or you work out more, obviously within healthy limits, right? And if you want to gain weight, the opposite. You have to eat more than you actually burn, right? This is the classical thing. If you're trying to bulk up or in the gym, or you're actually trying to lose, depending on if you're skinny or if you're more chubby, then you're going to have two different approaches. But at the end of the day, it's energy. So we need to make sure that the balance of energy, it's in order. Let's see more examples. Now, problem number 2 says that there is how much heat input is needed to raise the temperature of empty 20 kilogram vat. Let's say it's something like this, and there is this is the mass is 20 kilograms, and it's made out of iron, and we want to go from 10 degrees to 90 Celsius, right? So how much heat do we need for this? So part A says how much heat do we need for this? Well, if it's iron, of course, we're going to need the specific heat of iron. The specific heat of iron. Yes, specific heat of iron is 450 joules per kilogram per Kelvin, or per Celsius. 450, yes. So 450 joules. So the thing is, we want to warm up this thing, right? And it's empty, so the only thing we need to warm up is this. So how much heat do we need? This. What's the mass? 20 kilograms. What's the specific heat? 450. What is the change in temperature? 90 minus 10 again. It doesn't really matter if we're doing it in joules, or excuse me, in Kelvin or in Celsius, because what matters is the difference in temperature. So if you calculate these numbers, you're going to find 720 kilojoules. That's the heat that you need to warm up from 10 degrees to 90 degrees the vat. What happens, it says then, if instead of being empty, it's filled with 20 kilograms of water? What if it's filled with this being 20 kilograms? Now, here's the thing. We're assuming that everything is well, that's kind of bad, but it's in equilibrium, which means that if water is at 20 degrees and it's in equilibrium, Zero's principle says the vat is also 20 degrees. Excuse me, if it's at 90, the other one is at 90. Everything is at the same temperature. We're only considering equilibrium scenarios. We're not considering time dynamics of how heat goes. No. We have the beginning and end solution, and whatever happened there, we just don't care. We just care in the beginning and the end, right? And so we're just considering what happens if we want to raise this 80 degrees, right, or 80 degrees Celsius. So now what's important is we're going to have to add also heat for the water. So the total, let's first calculate that. So we want to heat water 20 kilograms, with water being 4.18. Remember, that's 1 calorie. That's the only one actually. I mean, it can produce that anyways. Kelvin, and actually it's going to be 4,000, right? 4,180, because this is kilograms. So that's going to be 4,180. By definition, 1 calorie is 1 gram. If we're going to 1,000 of those, because that's what makes a kilogram, I need 1,000 times more. So it's going to be 1,000 calories. And 1,000 calories is 4,180 joules, right? So what we're going to find is that this is 4,180, because it's a kilogram, 20 of those, times the increase in temperature, which is just simply 80. And if you make these numbers, you can calculate that to be 6,700 kilojoules. What's important though is how much heat do I need? Is this 6,700 kilojoules? No. What you need is 6,700 kilojoules to warm up the water, but you still need 720 kilojoules to warm up the vat. Because if one was colder than the other, then they will just start giving heat, the hot one to the cold one, to reach an equilibrium that will never be 90 Celsius. So very important, the total heat you're going to need is actually the sum of both. It's going to be 7 is the thing of the vat plus the heat of the water. And that's 720 plus 6,600, which is going to be 7,420 kilojoules. This is the right answer. Watch out for these systems. Whenever you have composed systems, make sure that you consider that each one of those needs to reach the temperature of equilibrium, both of them. Watch out, because otherwise you're violating conservation of energy. Important point to bear in mind for all these problems. One last thing that's very interesting in this discussion is something that we saw in the theory. We said that the heat that you need to achieve the same change in temperature depends on the mass, and it depends on the particular material. The particular material coming through a specific heat. How much energy do I need to raise 80 degrees 20 kilograms of iron is 720. But if I want to do the same amount of matter, which means the same amount of molecules, and the same amount of energy increase, I need actually, or the same amount of thermal of temperature increase, I need much more energy in the case of water. That comes through specific heat. So it's an important thing to observe. This is what we were discussing. It's going to depend on the amount of material. It's also going to depend on how much you want to achieve that. But it also depends on how much is the specific heat, because that's corresponding to the material itself. Let's see more examples now. Interesting problem now about realistic situation that you might relate to if you have done diving. So it says that there is a diver that jumps into the ocean, and then water leaks into the gap between the diver's skin and her wetsuit. And then it forms a layer about 0.5 millimeters thick, right? So we have gonna have the girl here wearing that skirt body, and then on top of the body, let's say there's this suit, right? Kind of. It should go through here, but basically that's the idea, right? And so the idea here is, let's say it just generates a layer which has 0.5 millimeters thick. Let's write that thing. And assuming that the total surface area of the wetsuit covering the diver is about, the area is 1 meter square, so the entire skin and everything is 1 meter. And the ocean water, when enters the suit, is at 10 degrees Celsius. Well, that's ocean, right? And it's warmed by the diver to skin temperature of 35 Celsius. Estimate how much energy is required by this heating process. This is kind of the idea of hypothermia, right? We will discuss towards the end of the process, but also the idea of the wetsuit. It allows some water to come in and kind of holds in there. The water is going to be warm up by your body, and that's going to be acting also sort of as a barrier for actually losing more heat, right? And regulating that. So, okay, basically, values that we need here, of course, is the density of water. We're going to take density of water to be 1,000. Well, it's salty water, so we're going to take it, okay, let's say that salt water is going to be 1,025 kilograms per cubic meter. So the first thing that we need to know is that we need to change heat. What's happening is that it's going from yourself, heat is leaving to the water. So we're going to have necessarily a negative heat, right? We're losing heat. That's just if we were considering the balance. So we're going to be losing energy. That's what you have to eat also, right? To produce that heat that we're going to lose. And so how much energy is going to be that? It's going to be that such that we take a certain amount of water, add a specific heat of water, and we raise the temperature how much? Well, it's going to be raised 35 delta T. So how much is delta T? How much we want to raise it? We want to raise it from we're going to raise it to 35 from 10, so that's going to be 25 Celsius, right? So that's going to be delta T. What about the specific heat of seawater? Well, that's going to be, how much is the specific heat of that? Yeah, we're going to take it to be, we're going to take it to be the same as water. So let's just say that this is 1 calorie, right? Which is going to be the same as saying that this is 4,180 joules per kilogram per Kelvin. Okay? and how much amount of water do we have in there? We don't know. So we're trying to find this, because what we have right now is that Q is equal to the mass of the water that comes inside the suit times 4,180 times 25. But here's the problem, how much is this? Well, we don't know how much, but we know something. This volume. It's equal to the surface area times the thickness of the layer. The area is 1 meter, the thickness layer is 0.5, 10 to the minus 3, because this is millimeters, so this is 0.5, 10 to the minus 3 meters, and that's going to give us 0.5, 10 to the minus 3 cubic meters. Important. What's the density? Density is volume divided, mass divided by volume. So what's the mass of the water? The mass of the water is the density times the volume. Typically, I mean, we know physics so we can go quickly, but in this case, as we should go is once we figure out we're missing the mass, we ask what equation has mass in of something I could have? Well, I have density, so what about density, mass over volume? And do I have volume? No, I don't, but I can calculate volume through here, so that's how you go, and then from here you go there, and from here you go there. Anyways, that's going to be 1,000 times that, which is going to be 0.5 kilograms, okay? So about half a kilogram, half a liter of water is going to be inside the body. Inside the body of the girl, right? She needs to warm up 0.5. So once we have that, we can just write 0.5 times 4,880 times 25, and that's going to be 52,000 or 52 kilojoules. So this is the amount of energy that we need to warm up the water. The question is asked in a funny way, because it says estimate how much energy is required for the heating by this heating process in units of candy or a candy bar. So let's pretend the classical candy bar has 250 kilocalories, right? The classical chocolate thing, like a Twix or something like that, is going to have, this is the candy bar, and we read the label, and the label says 250 kilocalories, or calories with capital of uppercase C, excuse me. So 250 uppercase calories is 250 kilocalories. So how many are these 52 kilojoules into kilocalories? Well, we know that 1 kilocalorie is 4,180 joules, right? So we can divide this by that, which is going to be 52, which is going to be, of course, 0.5 times, which is 12.5, right? So 52 divided by 4,180, that's going to be, then that heat, we can rewrite heat as 12.4 kilocalories. Now, if we take a bar to be 250 kilocalories, then we can see that in bars, we know that 1 bar, we're going to call it 1 bar equals to 250 kilocalories. Therefore, 1 kilocalorie equals to 250 bars. And so we can convert that by dividing 12.4 on 250, which is going to be 1/2, and that's going to be probably about 20, something like that. 4 divided by 250. Yeah, okay. 5 10 to the minus 2 bars, or 0.05 bars, which in entire unit, that's how much? That's 5% of a bar. Yeah, a tiny little bit to warm up the water. This is just a silly example, but the idea here is that units anyways are arbitrary, and that of course you can define this in terms of units that are more convenient to you. In our day-to-day we work with kilojoules, if we're in food we work with kilocalories, but we could think of a world where we define the standard of kilocalories maybe, right? And so Soylent Green, and we know the amount of a portion of Soylent Green with the famous science fiction movie. Anyway, and so we can calculate how many of those portions we would need to actually achieve certain tasks. So conservation of energy at the end of the day, and also increase in calorimetry. Let's see now some more complicated examples, combining more things and more materials, but basically the same idea. To measure heat transfer, we use calorimeters, and those are the particular setups that allows us to make these measurements accurately. Now you may be wondering how on earth can we define energy of some candy bar or spaghetti or whatever you think of, some food. And here's the idea. You can use a calorimeter, but a particular one, which is called a bomb calorimeter, which was the one that is established to measure precisely how much calories some food has. And the idea of this device is, and how it's used in real world, is the one that problem number 10 in discussions targets. So it says estimate the calorie content of 65 grams of candy from the following measurements. It says that when you put, first measurement, let's say, when you put, let's call M sub 1, 50 grams of that sample in a small aluminum container of mass 0.325 kilograms, 25 kilograms, filled with oxygen. You put everything together and you put this inside water. So this makes like, this is your candy bar and this is the aluminum thing, right? Obviously it's closed and there's some oxygen inside here, right? That's the idea. And we're going to submerge this into a bath of water that has a mass we're going to place this. Let's be careful. Let's place this. Okay, so we have the sample inside here with the oxygen, okay? And this container is placed on 175 kilograms of water. In another aluminum, it's going to be, let's say, aluminum bath, right? And the second aluminum, we're going to call this Al2, it's equal to 0.624 kilograms. And this is at an initial temperature of 50 Celsius. The oxygen candy mixture in the small container is ignited, and the final temperature of the whole system, the equilibrium temperature, it's 53.5 degrees Celsius. How can you figure that out? Maybe put the thermometer in here, measure the temperature of the water. The temperature of the water in equilibrium is the same temperature as the aluminum thing, is the same as that aluminum and that thing, because that entire thing is going to be submerged, which is the temperature of the burned sample. So how much is the where is the temperature coming from? It is coming from precisely burning that piece of candy. That is the idea. And so that is going to release heat to warm up this, which is going to warm up the water, which is going to warm up the container. So what we're going to have to do is a balance of heat. All the heat in the system, all the heat required to do that. And heat, of course, is going to be equal to mc delta T. Right? Now we're going to have to find the specific heat of aluminum and also a specific heat of water. We know the specific heat of the candy, call this C, and then let's call this C for candy. And we're trying to find this C of C. What's the specific heat of the candy? That's the experiment of a bomb calorimeter, right? A bomb calorimeter. Okay, that's the idea. So we're going to burn that thing and figure out what's going on in here based on how much heat this needs, because we know how much heat we need to warm up that water that much, right, for instance. So then we can figure out these things. Let's see also the specific heat of aluminum, which is the specific heat of aluminum is 0.22 joules per kilogram per Kelvin. Okay, so here's the thing. Where is the heat coming from? It's heat from the candy. So I'm going to have a candy, which is going to give the heat to what? To the aluminum and the water. But important is want to warm up this aluminum, but it's also want to warm up that aluminum. So then we have to consider the entire mass of the aluminum. And each one of these is going to take a portion of the heat. So what we can do then, where this is Q aluminum 1 plus Q aluminum 2 plus the water. So what we need to do is the balance of all the heats. So the heat of the candy bar of the 50 grams is going to be mass of aluminum, specific heat of aluminum, times the change in temperature plus the mass of water, specific heat of water, the change in temperature. Change in temperature goes from 15 to minus 33, so that's going to be 53.5 minus 15, which is going to be 38.5. let's say Kelvin, okay? And so the mass of the aluminum is how much? The mass of the aluminum is 0.62, so 0.624, but plus the calorimeter glass, right? So that's going to be 0.323 to find. It's not, of course, not the glass cup. So 0.325 kilograms times 0.22. Oh, this is in kilocalories. So this is in kilocalories. So this is in kilocalories. I made a mistake. That's in kilocalories. So we can convert that or keep it in kilocalories and get the result in kilocalories anyways. That's okay. So let's say kilocalories to make it more convenient, because if we work in joule, we're going to have to convert it to kilocalories, which is the uppercase cal for food, and this is food, right? So we're going to keep it at 0.22, but then the specific heat of water is going to be 1 kilocalorie per kilogram per Kelvin. Kilogram per Kelvin, right? So 1 kilocalorie per kilogram per Kelvin for water, which actually makes everything much more convenient. So then it's going to be 1, how much is the water? Is 175 times 1 times temperature change, which is 38. So we missed something here. We missed 0.38.5. No. Sorry. Let's do this. I don't know why I'm saying 38.5 Kelvin. Right, I have factored this. It's the same change in temperature. The mass is different and the specific heat is different, but I can factor out the temperature. Anyway, from here we're going to get this is 9, so it's almost 1, so that's going to be, let's say, 21, something like that. And that's going to be 175. So this, let's say, is approximately 196. How much is this? And that's going to be times 38, right? So that's going to be 196. This square bracket is 196 times 38.5, and that gives us the total of about 75.4 kilocalories. So how much is the heat of 50 grams of the candy bar? It releases 75.4 kilocalories. Now the question is, how much energy does 65 grams have? We can probably make this thing in here. So to warm up 15 grams, to burn 15 grams, or 15 grams contain heat enough as 75.4 kilocalories. So how about 65? That's going to be 75.4 divided by 15 grams is going to give us about 5 kilocalories per gram. So how about 65? Well, heat for 65 is going to be 65 of those 5 calories, which is going to be 325 kilocalories, or uppercase calories, 325. So as how to calculate the energy content of a candy bar. We use a bomb calorimeter. We're going to burn it, and the heat released from that is going to be transferred to the environment. We're going to be able to measure the equilibrium temperature. We're going to be able to measure how much heat has been released, because we of course know the specific heat of our water and aluminum containers, and then we can figure out how much is this sample. We carefully weight it. We figure out it's 15. Then we have a value for every calorie. And so whatever is the sample size, then we can just multiply it and get it. Bomb calorimeter is energy content of food. Let's see some phase change. Let's see a problem now on latent heat, which is adding an extra layer. The critical point to solve any change of phase calorimetry problems is to realize the change in phase happens at a particular point, at a given set of pressure conditions, right? Which we assume in this course at least to be environmental pressure. So, excuse me, ambient pressure, so atmospheric pressure, right? 10 to the 5 pascals. You're going to have to remember the plot. If you have heat and here you have temperature, first you're going to have to raise the temperature to the melting point. Then you're going to have to provide enough energy to transfer it, raise, and melting point. So do not forget this transition. These ones are latent heat. And those play a role as soon as you reach the temperature of evaporate, in this case the temperature of the melting temperature and the evaporation temperature, right? Okay, fusion and evaporation temperature. Up to that point, use specific heat. At that point, use latent heat. So that's going to be the key. And it's a very interesting idea that we observe that we can see in problem number 12. It says high altitude mountain climbers do not eat snow, but always melt it first with a stove. To see why, calculate the energy absorbed from your body if you, and there's two scenarios. First, you eat 1 kilogram of, which is a liter, right, of minus 15 Celsius of snow, which your body warms to body, which your body warms to body temperature of 37, right? So we're gonna warm up to 37 Celsius, and we're gonna take 1 kilogram of ice, and the temperature is minus 15 Celsius. And we're gonna see how much energy we need in here. That's gonna be a scenario A. So let's try actually first solve part A. So how much energy do we need? There's two things we're gonna have to go. We're here. We're at minus 15 degrees. The fusion temperature is gonna happen at 0 degrees. So we're gonna have to account for a transition from minus 15 to 0 degrees plus some heat required to go melt plus the heat required to go from 0 to 37. Here we have ice, here we have the water, well, it's always water anyways, and here we have the mixture. So this is the scenario. First, we're in the solid, we're going to have the mixed, and we're going to have the liquid. And so that's going to be the end point. So we're going to have to raise the temperature, we're going to have to convert the entire material, we're going to have to raise the temperature to our final point. So careful with these calculations. Final heat is going to be mass and a specific heat of ice and water. The water is going to be 4815, right? So that's going to be specific heat of water is, we have seen this a million times, joules per kilogram per Kelvin. Specific heat of ice is going to be 2100 joules per kilogram per Kelvin, and latent heat it's going to be 333 so actually no, it's 3.33 joules per kilogram. That's it. Okay, that's the fusion latent heat. Okay, which is basically how much energy we need to break the bonds of the solid crystal to become liquid, right, per kilogram. So the first we're going to start. How much mass we take is always the case, is always the same. But basically we're going to have here water times the temperature from going from minus 50 to 0. We're going to have the mass times specific heat, which is going to be, latent heat plus mass times, now is water, this is ice, apologies, this is ice, times the increment in temperature. But now the increment in temperature is going from 0 to 37. And now we can start. We can see the mass, we can factor it out. So it's 1 kilogram anyway, so we don't even need to factor it out. It's 1 kilogram times the specific heat of ice, which is 2100, times the increase in temperature. How much is the increase in temperature? Going from 0 to 50 is going to be 0 to minus 50, which is of course 15, plus the mass is 1 kilogram, and this is 333. By the way, this is 10 to the 3, 10 to the 5. 10 to the 5, sorry, 333 10 to the 5 plus 1 specific heat, now it's going to be 4000 times 37 degrees minus 0, which is of course 37. If we make all these numbers, so if we make this, it's going to be, that one is going to be 0.315 10 to the 5. This one over here is still going to be 333 10 to the 5. And this over here is going to be 1.54 10 to the 5. And so we add together. You can see from here already that the most of the heat required is actually for this, for melting the ice. This is melting the ice. This is warming the ice. And this is the warming of water. So by far, also because we are increasing the temperature of water quite a lot, takes more to warm up the water, where we can already see it in here, right? Compare the specific heats and the cases. Anyway, so when we add all together, that's going to be 5.2 10 to the 5 joules. So it takes to do this process 5.2 10 to the 5, which is 520 kilojoules. Now the next question, however, is what would be the case if instead of eating this, you were to melt it first using a stove and then drink the 1 kilogram of water at 2 degrees. So in that case, what we're actually asking for is what happens, what's the heat from our body. If we warm it up and then we drink it, then we do not need to raise the temperature of the ice, and we do not need to change this temperature. So basically, we're just going to be concerned about this. Now there's a slight change. The temperature is going to be from 0 to 37. It's going to be from 2, so it's going to be slightly less than that, right? But we can already see it anyways. Q is going to be just mass of water, specifically water, and the delta T, which is going to be 1 kilogram for 180, and the difference in temperature, which is going to be 37 minus 2, which is 35, and so that's going to be 1.5 10 to the 5 joules. So the difference is huge, but we could already see it in here. If you warm up with the stove, most of the heat, which is the most important part of the heat, is taken care of by the wood or whatever you're burning. If you eat the solid is going to raise the temperature, convert into water, and finally reach the body temperature, because your body needs to be in equilibrium. So you're wasting all this energy from, all of this heat from your body into melting the snow. So you're actually losing heat. And if you lose heat, we can calculate what will be the drop in temperature in your body as a result of wasting all these 3.7 10 to the 5 joules per kilogram, right? That we are, or joules, excuse me, that we are actually burning to warm up. So that's the reason why you do not do this. You do not eat snow. You warm up the snow, you melt the snow, and then you drink it. And as little as you can, even if it's very cold, drinking it as a liquid and an ice can be the difference between death and life. And of course, putting aside the fact that you can burn yourself eating snow anyways. But that's a different discussion. Very important to see then, when we're having latent heat, you have to apply latent heat only in the range of temperatures, at the fusion or at the evaporation point. Not before, not after. Before and after, you describe everything with a specific heat. And these are the problems for calorimetry.